Okay, good morning, everyone. Hope you're all well. Onward with crossing the reality gap and open challenges in the field of evolutionary robotics. I just wanted to check in with you all about the assignments. So you're now working on the 10th and final assignment, which is the quadruped. You've been working with a simple robot up to this point. We're going to work on the body this week. Next week, on next Tuesday, you will have finished all 10 assignments and you will have the foundation for you to start venturing out on your own in evolutionary robotics. So you'll have about a month's time for your final project, and I will set aside a good amount of time on Tuesday to talk about the final project, what it is, what Amanda and I will expect from you during that month, and what you can expect from Amanda and I. Okay, that's the final project. Just to check in with the quadruped project. Right at the beginning, I put a little bit of housekeeping. Just as a reminder, you have two processes that are talking to one another now, search.py and simulate.py. They're communicating back and forth using files, which is admittedly not the best way for them to communicate, but is the simplest and quickest way to code this up. So hopefully most of you have resolved all of your file timing issues, and you now have search and simulate talking to one another relatively well. If you still are having a problem, please come and see Amanda and I. Jonathan asks, what should we be submitting for the quadruped? I remember now that I forgot to add in a request to upload a video at the end. For the lucky few that are already at the end of the quadruped assignment, you're a little bit ahead of me. You can probably guess what it is. I just want you to capture a few seconds of your quadruped jumping around. So I will put up, when we finish today, I'll add a couple of items to the end of the quadruped assignment telling you to do exactly that. And as usual, upload the resulting video to YouTube, capture the YouTube URL, embed the YouTube URL in a Reddit post, get the URL of the Reddit post, drop the Reddit URL back in Blackboard. So nothing too surprising there, but thanks for the reminder, Jonathan. Okay, so again, the two processes are communicating back and forth with files. Simulate.py can write out various messages to the console, and search is, not surprisingly, writing out the results of search. You want to see the values of all of the fitnesses of the parents and children. Simulate.py is maybe writing out messages about PyBullet or other aspects of sensors or motors or the neural network. But when these two are communicating, they're both dumping their messages into the same console window and everything's getting mixed up. So on a Mac or a Linux machine, you can use this somewhat cryptic term here, and you can embed this inside search.py, the search.py hierarchy, where you start up simulate.py. You should be able to put that in, and that will suppress all of the messages. It'll suppress all of the messages being output by simulate. It's dumping them sort of to null. It's just basically getting rid of all of those messages so you don't see them, and you will only see the fitness values or whatever else you're printing in search.py. I was doing a little bit of reading this morning. I think this works on a Windows machine as well. If anybody has a Windows machine and tries this out, let me know whether this works. I'm a Mac person, so I can't test this myself. Let me know. And I think this should be a solution that works for everyone. Okay. Any other questions about assignment 10 before we dive back into the reality gap? Going once, going twice. Okay. All right. So we've got one or two slides left in lecture 15 where we're talking about the very first attempt in robotics to cross the simulation to reality gap back in the 90s, which used a relatively intuitive idea, which is noisify the simulation. This is still used today in state-of-the-art sim-to-real, and we'll spend most of today talking about the Golem Project. Okay, so So just to back up again, we have this simulated robot that is moving through a T-maze. This is not using a physics engine. This is using basically a lookup table. It's about as simple a simulation as you could imagine. And they broke the T-maze into the stem of the T, the top of the T. And one of the most important concepts to take away from this lecture series, this lecture set of slides, is this idea of completely noisifying aspects of the simulation that are difficult or impossible to simulate. It is next to impossible to simulate how infrared sensors will behave when the robot is sitting near the T junction. So the idea here is don't even bother simulating it. Not only get rid of the junction altogether and break the T into two pieces. Okay, they also sprinkled noise on other parts of the simulation. What do I mean by sprinkling noise? Well, they slightly varied during evolution lots of aspects of the simulation, such as which side of the stem of the T does the light come from, the width of the corridor, the starting orientation of the robot as it points up the stem of the T, and so on. We talked a little bit about the neural network last time, and I left you with a little thought experiment, which is the T-maze was designed decades and decades earlier by animal behavioralists to study how or whether animals use memory, where the idea is the animal should remember which side of the corridor the light came from, and by the time the animal or the robot gets to the junction, it can no longer see the light. It needs to remember and turn in that direction. We saw last time how actually, if you think carefully about embodiment, animals and robots can cheat at this task and they can solve the T-maze without memory. Nonetheless, this neural network was built so that if evolution decides to evolve a controller for the robot that does remember where the light is, it's possible. We've looked at a fair number of neural networks in this class so far, and usually it's hard for us to localize within the neural network where the memory is or where the triangle recognition unit is, and so on. This neural network is an exception. You can actually visually see where the memory resides in this neural network, and I apologize, I forgot who it was last time, but somebody hit on the right answer just before we ended. We have our ambient left light sensor over here and our ambient right light sensor over here. And if you look carefully, you'll notice that there's a dashed line going from this one to this one and another dashed line going from this one to this one. The dashed arrows represent inhibitory links. So inhibitory synapses or inhibitory links are those that have a negative weight associated with it, meaning the more strongly the presynaptic neuron fires, big positive number times a negative number is a big negative number. It's inhibiting this neuron. If the presynaptic neuron's value is near 0, 0 times a negative number is a number that's very close to 0, and it has less inhibitory influence on the postsynaptic neuron. You'll notice they enforce bilateral symmetry in this neural network, so there are inhibitory connections going back and forth between the light. So to build up our intuition of neural networks, I want you to imagine this neural network sitting inside the robot. The neural network causes the robot to start driving up the stem of the T, and let's imagine that the light flashes from the left. At that moment in time, there is more light falling on this sensor than there is falling on this sensor. So this sensor neuron's value is larger than this sensor neuron's value. As the robot moves forward a little bit, what happens at this next moment in time? Tell me about these two neuron values at that next neuron moment in time, just after the robot moves past the light. Anybody have any ideas? When the robot is next to the light, this neuron's value is larger than this neuron's value. So the robot moves forward. What happens? Let's imagine a simpler way to think about this, if you're still thinking about it, is let's imagine the robot's moved forward, and let's imagine now the light has turned off. So now the robot is in complete darkness. Tell me about these two sensor neurons. So at the previous time step, this sensor neuron's value was larger than this sensor neuron's value, which means this larger value times this negative weight, it is more strongly inhibiting this sensor neuron than this sensor neuron is inhibiting this sensor neuron. This sensor neuron was further from the light during the previous time step, so its value is nearer 0 than this value. Smaller value times a negative number means less inhibition over here. So at the next time step, this neuron is inhibiting or pushing down, pressing down this neuron's value to be closer to 0 or maybe even negative. So there's sort of a tug of war going on between these two neurons, and this neuron is losing. So this neuron's value at this next time step after the light has turned off, this sensor neuron is no longer receiving any value from the ambient light sensor. Neither is this sensor neuron, but these sensor neurons are receiving input from other neurons. So this sensor neuron inhibits this one less. This one is less inhibited, so it inhibits this one more strongly. This one is now weakened even more, so its ability to inhibit this one is weakened even more, which means this one is even stronger. Its value is actually growing. It's getting a larger positive value times a negative number. It's pushing this one down, and eventually it will saturate. If the range of values for these sensor neurons is between, it doesn't specify here, it could be 0 and 1 or 1 and -1. The one on the left's value goes to its maximum value, and the right-hand sensor neuron goes to its most minimum value, and it's going to stay there. There are some synapses coming in from the motors, from the motor neurons, but we're just going to ignore those for now. So basically, once the light flashes, there is a slight asymmetry in the light levels, and then this mutual inhibition causes that difference to grow and saturate and stay there. It would take a very, very strong light on the right-hand side to break that asymmetry. That is where the memory is. This is a common neural circuit that's actually seen in animal nervous systems as well. You have individual neurons that mutually inhibit one another, or whole neural circuits that mutually inhibit one another, which produces this sort of interesting pattern where slight differences become reinforced and magnify. It's a very simple way in a neural circuit to record information or mentally magnify internally what were sensed as slight differences. Okay. Obviously, the focus in this lecture is not on neural networks, but again, just kind of an interesting detail of this work. Again, this work was done back in the 90s, so I apologize for the image quality here. There are no simulation videos because there's really no simulation. They're just lookup tables. But evolving these neural networks and evaluating them in a simulation built from lookup tables produced an evolved controller that, when put inside the physical Kepra robot, remember the Kepra is this hockey puck type robot. When they took some of these evolved neural networks and dropped them into the physical Kepra robot, not only did the physical Kepra do the right thing. When the light was on the Kepra's left, the Kepra would consistently turn left. You can see they put a little LED on the top of the robot so they could record in a darkened room the trajectory of the robot. And then if they took the same evolved controller and ran that controller multiple times on the physical Kepra and put the light on the right, the Kepra consistently turned to the right. You'll notice the difference between this pair of images and this pair of images is that the T corridors themselves are wider. So the robot is also robust to changes in its physical environment. Heraclitus told us that man never enters the same river twice. And this particular evolved controller succeeds when it's placed in different T mazes more than twice. That wasn't very elegant, but I think you get the idea. Okay, so the difference down here is they widen the corridor again, and you can notice that they did multiple trials with the same single evolved neural network. Sometimes they placed the Kepra here and was facing in this direction, facing towards the right wall. Sometimes they placed the Kepra here and was facing a little bit towards the left wall. But again, it was robust to initial orientation and successfully solves the T maze. This was the first demonstration of training a neural network in a simulated robot, taking that evolved controller and dropping it into the physical robot and having some success. This was a very exciting result back in the 90s. Okay, so that concludes the first attempt to cross the reality gap. We're now going to fast forward in time to 2000 when the Golem Project was published. The Golem Project the Golem Project attracts significant attention, so much attention that it actually appeared on the front page of the New York Times. You can see the date here. According to the reporter, scientists had reported that they had made a robot that makes its own robots. So what do they mean by that? Well, we're going to talk about this particular paper today that was reported on by the New York Times. This was an attempt to cross the reality gap, but in a different way from what we just saw. In the 90s, the only thing that was really possible was to transfer evolved neural networks from simulation to reality. By 2000, Lipson and Pollack had a physics engine. They were evolving virtual robots in the physics engine. But instead of transferring just the evolved controller, they evolved the body and brain of the robots in simulation. Here's one of the evolved bodies here. And they transferred the entire robot to reality. They transferred the evolved body and the evolved neural controller. How did they do so? Well, once they had an evolved robot, the physical structure of that robot, they built the physical structure of that robot using a brand new machine in 2000, which was known as a 3D printer. So this paper is about a lot of things. One of them is the reality gap. The other thing that really impressed people at the time was this sort of dramatic demonstration of the potential of 3D printers. Okay, so at the time, 3D printers could only print plastic. We'll talk about what they can do nowadays in a few minutes. So in this experiment, you'll notice that the robot is made up of a whole bunch of cylinders. These are hollow cylinders. They printed these hollow cylinders using a 3D printer, and it only printed the plastic outer casing of these plastic cylinders, and then they manually plugged in the motors and the electronics, which you can see here. So this wasn't quite an automatic process, but it was an important step forward in the following sense. Evolutionary robotics is usually about automated design. Can we automatically design a robot that does something? Usually we're designing it in simulation. 3D printers, when they're coupled to a simulator and an evolutionary algorithm, provide the promise of automated manufacture. So this project was meant to demonstrate, again, not just crossing the reality gap, but an attempt to automate robotics. Automate the design of simulated robots and then automate their manufacture. The idea here, the way to cross the reality gap is maybe not to worry about crossing the gap itself, like we just saw in the noise project, but evolve hundreds or thousands of millions of simulated robots. And if 99% of those designs don't transfer to reality, doesn't matter, as long as a few of them do. if we cross the gap enough times, we should start to collect in the real world enough physical robots that reliably do what we wanted them to do in reality. Okay, that's sort of the vision for the Golem Project. Let's dive into a little bit about how this works. The reporter here mentioned robots making its own robots, which is not strictly true. We have the robots themselves, and the other robot mentioned in the title here is meant to be the 3D printer. So the New York Times reporter was viewing the 3D printer itself as a robot that was making the evolved robots. Kind of an interesting idea. This idea of robots making robots has also been around for a very long time. The original idea dates back to the Second World War, or just after the Second World War. And the idea came from John von Neumann, a pioneer in computer science. Nowadays, he had this thought experiment of perhaps sending robots to the moon or Mars. Once the robots get there, they would start mining for materials, and whatever mined materials they found, they would stitch and weld those raw materials together into a copy of themselves, and you'd have a self-replicating robot swarm. This is where the idea came from, and obviously Hollywood has had a lot of fun with this idea over the years. This is still relatively, this is still basically science fiction. Nobody has really managed to create self-replicating swarms per se yet. But robot technology is moving forward. This may be a possibility in the not too distant future. Okay, so in this cartoon here, which was actually taken from a 1980s NASA report, shows this idea where design and manufacture are kind of blurred. So obviously this cartoon here is meant to be a robot, but it's also somehow a 3D printer. It's something that's printing or making, in this case, a copy of itself. So a lot of different ideas, a lot of different robotics ideas that are mixed up here. You'll notice I put in quotes here von Neumann machines for all the students of computer science here. You should also know about the von Neumann architecture. The von Neumann architecture is the basic computer architecture that's found in most PCs and laptops and even phones these days. It's a particular kind of computer architecture. Von Neumann machines are something different. Turing also has two sort of memes attached to his name, the Turing test and the Turing machine, both of which we talked about in this class. Okay, so two founders of computer science, both of them had many brilliant ideas, but each of them had two ideas that kind of took off. There's the von Neumann architecture, which has become reality, and von Neumann machines, which remains for the moment still in the realm of science fiction. Okay, back to the Golem Project. Let's walk through exactly what they did. Like some of the other experiments we've seen so far, I'm going to break this down into sort of 3 experimental steps. Step 1 is going to look very familiar to you. In a physics engine, they evolve a robot to locomote. But unlike what you're doing at the moment in your assignment, they're going to evolve both the body and brain of the robot simultaneously. Here's the body of the robot, and here's its neural network brain. And you'll notice that 2 of the neurons are attached to the robot's body. These 2 are the motor neurons. We'll talk about them in a moment. Once they've evolved the body and brain, for a while they take the one that has the highest fitness and they manufacture a copy of that robot using a 3D printer. And then they manually had to snap in all the other things that couldn't be 3D printed at that time. Okay, let's have a look at the genotype. How did they encode a description of the robot's body and brain? We've looked at lots of different ways of encoding genotypes so far. When we first talked about genetic algorithms, remember that genetic algorithms encode their solutions as a vector of numbers. This is not that different from what you're doing in the assignment, where you have a list of numbers corresponding to the synaptic weights for your neural network. We looked at genetic programming, a different kind of evolutionary algorithm that encodes the genotype as a tree. In this case, we are looking at a genotype that encodes a list of lists. So there is the master list called robot. That list is made up of 4 other lists. If you remember back to the NEAT algorithm, the NEAT algorithm also had a similar genotype. It was a list of 2 lists, or it contained 2 lists, the list of descriptions of the neurons and a list of the descriptions of the synapses. This genotype has 4 lists inside it. The first list is a list of triples, XYZ triples, which represent the vertices that make up the robot. So this one has 1, 2, 3, 4, 5, 6, 7, 8 vertices. So this vertices list would have a length of 8, and each element in that list would have the X, Y, and Z coordinates of that vertex. Pretty straightforward. The next list is a list of quadruples of 4 numbers. The first 2 are integers, indicating which 2 vertices in the vertices list that bar connects together. So here's a bar connecting these 2 vertices together. And then it specifies relaxed length and stiffness. Does anybody have any idea what that means? Where have we seen relaxed length and stiffness before? Anybody remember? When we talked about the evolved passive dynamic walker that walked down the declined plane. Logan's got it, right? This is a suggestion that there must be some spring involved in each bar. It's not shown in the cartoon here, and I don't know if you can actually see them in the physical. You can't see them in the physical robots here, but some of these bars have a spring placed in the middle of them that allows the bars to increase and decrease in length if they are pulled and pushed on by their vertices. The stiffness, as you'll remember, is a floating point value, where a low value represents a slinky, something that's very loose and doesn't take a lot of force to increase its length or decrease its length. The relaxed length is the resting length of the spring. So left to its own devices, if there's no forces acting on the spring, how short or how long does that spring want to be? There's another parameter associated with springs that isn't mentioned here, which is damping. Maybe they set that value to be constant across bars. You'll notice that some of the bars here, actually in this particular example, all of the bars do not have springs in them. So the evolutionary algorithm could set this value to be infinite or a maximum value. Maximum stiffness is a rigid bar. If you imagine a spring that's made out of very thick enough steel, there is no force in the universe that's going to pull or push it apart, or no reasonable amount of force. So this allowed evolution to add or remove springs in the bars. Okay. The third list is a list of neurons, and for each neuron in the neurons list, we specify a threshold for the activation function. So if the raw value arriving at the neuron is above this threshold value, the neuron outputs a positive value. If the raw sum coming into this neuron is below this threshold, it would output a 0 or a negative number. It's not specified here. It's not really important for our purposes. This is a little confusing. In the second part of this neuron element are synapse coefficients of connections to all neurons. So it's assumed in this neural network that every neuron is attached to every other neuron. So in this cartoon example here, where we have 5 neurons, the length of the neurons list would be 5. And there would be 5 numbers in here plus the 6th number threshold. So each neuron would have 6 numbers in it. The 5 numbers here represent the strength of synaptic connections, the strength of the synapses that are leaving this particular neuron, this presynaptic neuron. There are 5 outgoing synapses Four outgoing synapses, and the fifth one is a self connection, which is not shown in this cartoon. Okay, so we got all the synaptic weights in here. And then finally, the fourth list here is a list called actuators. And each element in the actuator list is an actuator. And each actuator is described by 3 numbers. The first number is an integer, which indicates which bar that actuator is attached to. And again, I'm going to back up to the physical robot. Here's 1 bar here, and you can see there's a motor in here. Here's a second bar and a third bar, each of which has a motor attached to it. So in this case, there would be 3. There are 3 actuators on this robot. The other bars have no motors associated with them. Okay, so that's the bar index, and then there's also a neuron index. So an actuator requires an input signal. The actuator needs to know how much force to apply. The actuator knows how much force to apply by getting that value from a motor neuron. So these wavy lines here, these are represented by the actuators here. They connect a neuron in the neural network to an actuator embedded in a bar of the robot's body. The third number, bar range, what I forgot to mention is these are linear actuators or pistons, which can increase or decrease the length of the bar. It's a little difficult to see in this picture. I'll show you some videos in a moment, but as you can already kind of see here, these pistons increase or decrease the length of this piece, and this piece. Okay. There are no sensors in this robot. So is this robot controlled by open loop control or closed loop control? If there are no sensors and we're just going to get motor neuron values, the robot is just going to do some action over and over again. Is this open loop control or closed loop control? Alex says closed loop control. Remember that closed loop control actually requires sensors. You get some sensor values. They influence the motors. The motors cause actions which change the relationship of the robot with its environment. That changed relationship with the environment often changes the values of the sensors, which change the values of the motors as it flows through the neural network, and around you go with this closed loop. Open loop control is we don't have that feedback loop through the sensors. The motors just send their value and the robot does its thing, but whatever the robot does not affect the new values of the motor neurons. So this robot is actually controlled by open loop control. But how do we get this neural network going? What is sort of the input to this network that gets the motor neurons to start changing values? They include a central pattern generator, which outputs a pulse of values. The central pattern generator stimulates one or more of these neurons, and I don't know if it's actually described in the paper very well. That's why I placed a question mark after here. They mention that they evaluate each simulated robot in a simulation. They didn't mention how many time steps they run their simulator for. They just said for a fixed number, 12, of cycles of its neural control. The way I interpret this is, and again, it wasn't clear, the authors could have been a little more clear in their writing here, is the central pattern generator emits 12 signals, which causes 12 changes in the values of the neural network, which causes the robot's actuators to extend or contract at some rate, at some pattern, and they repeat that pattern 12 times. It's a little unclear, but that's the idea. So this is open loop control in this case. Okay, so let's talk. That was the genotype. Let's talk a little bit now about evolution. They start in the first generation not by creating random genotypes, but creating 200 null genotypes. This is kind of odd. You don't see this very often in evolutionary robotics. They set this list, this list, this list, and this list to have 0 length. No vertices, no bars, no neurons, no actuators, which is kind of odd. Means by definition we have these null genotypes that produce null phenotypes. No vertices, no bars, no neurons, nothing. An empty robot or a null robot. Fitness is displacement of the robot's center of mass. So we know these 200 genotypes are going to get 0 fitness. Null robots don't do anything, therefore they don't displace at all. In this case, they're going to rely on mutations, which are going to mutate some of the null genotypes from the first generation to produce random non-null robots in the second generation. Kind of odd, but maybe just a detail. Okay, so in this case, they used 10 different mutation operators. So what do I mean by a mutation operator? We've looked at, in your assignment at the moment, you only have one mutation operator. That mutation operator randomly changes one randomly chosen synaptic weight. That is one type of operation in which you can vary the genotypes in your parallel hill climber. When we talked about neat and hyperneat last time, we introduced crossover, and crossover is a type of variation operator. So when we use the term variation operator, we're talking about all the different operators that can vary or randomly change or mix up genetic material in the evolving population. A mutation. Sorry, not operator, operation. Mutation operation and variation operation. The mutation operation is, again, just a type of mutation, right? It's related to just one parent producing one varied child. In this case, they have 10 different types of mutations or mutation variations. At every time when one parent produces an offspring through mutation, they randomly choose one of these 10 variation operations. So they roll a 10-sided die, and whatever number comes up, that's the mutation operation that they apply. It's a weighted die. Some of these mutation operations have a higher or lower probability of occurring. Anybody see why some of these mutation operations are more probable of occurring than others? They made some mutations rarer than others. Why? If you have an idea, go ahead and type it into chat. Okay, maybe let's come back to this question if you're still thinking. They're less expensive. Matt, what do you mean by less expensive? You can unmute yourself and elaborate if you want.
Yeah, so if you split a bar into and add a vertex, it's like more resources to do that compared to just changing the length of a bar or changing a synaptic weight. So ideally, they use less resources to create a more efficient robot.
Yeah, that's a good point. So it could be some of these are less expensive, require less resources. You're adding more material. If you're adding more material, like adding a dangling bar, what is the impact of using that additional resource? We have a parent, and now we have a child that has an additional bar. Aside from the fact that the child is now using more materials, in naturally evolving populations, obviously that is literally an expensive operation. The child has to metabolically maintain that additional physical mass. That may not matter too much in this case. Maybe it does. The robot's maybe now just going to be heavier and has to carry that stuff around. Imagine a parent that has medium fitness. It's doing okay. It's moving forward a small distance, and it produces a child that has a randomly dangling bar off it. What's the likelihood that that child is going to move as quickly or more quickly than the parent?
probably pretty unlikely.
It's pretty unlikely, right? So that's a pretty big mutation. So generally speaking, the larger the effect of a mutation, the more it changes the child, the less likely that mutation is going to be beneficial. I think it's Fisher's law in biology. Someone's going to have to fact check me there. Ronald Fisher was an early geneticist and an early biologist who stated this somewhat obvious idea if you think about it. So some of the smaller mutations, things that have a smaller impact on the phenotype, the body and brain of the robot, these are more probable. So slightly lengthening or slightly shrinking a bar intuitively is going to produce a child that moves more similarly to the parent than adding or removing a bar from the parent. Okay, so here's a cartoon of what's shown here, or not shown here, is a null robot. There's nothing. And then the black arrow represents a mutation chosen from this list that turned the null robot into this robot. This child then produced this grandchild produced this great-grandchild, and so on. So I want you to have a look at these 1, 2, 3, 4, 5, 6 arrows. And for each of these arrows, tag each arrow with one of the numbers from this list of 10. So you can probably see here, this one's pretty straightforward. We go from null to suddenly a bar being there. So that's mutation number 5. We randomly added, number 3. We added a dangling bar off of a null robot. We added a bar, and then off we go. So if you have an idea, go ahead and type it into chat. For example, I could type this, which would be my guess that we started with mutation operator 5. The grandchild was produced by mutation operation 6, and so on. So go ahead and think that over. And if you have an idea, go ahead and type your list into chat. I should say that some of these arrows, I think it was not... we've done this in the past, and I think students have correctly identified that for one or more of these arrows, that you actually have to apply more than one mutation operation. So you can write that like that, if you like. I'll give you a minute to work on that, and type your idea and type your guess into chat. Okay, give you 5 more seconds. Okay, Hannah has an idea, Missy has an idea, Logan has an idea, George has an idea. I already see some commonalities and some differences. Okay, so we know that the first mutation is number 3, which Hannah, Missy, and Logan have in their solutions here. The next mutation at this step, number 1, change the length of the bar, so 3, 1 makes sense. Next one, the bar gets longer again, so we know it's 1 again. We notice a neuron has appeared. So at this point, we have operation 1, change the length of the bar, and number 5, add an unconnected neuron. So I see 1 plus 5 in some of your solutions there. What about this step? If you did not type something into chat, just go ahead and type it in now. Is this mutation operator 3, 7, 4 plus 6? What's happening? What mutations are being applied to change this robot into this robot? What's happening at this step here? I'm looking at some of Hannah's and Missy's and Logan's and George's entries here. I think I see at this step, George has 1, change the length of the bar, plus 5, add an unconnected neuron. This is the one here. And we're missing 1, 5, and 9. Attach or detach neuron to a bar. Not quite. These neurons are not connected to the bar yet. There is a synapse that's been added here, and I apologize if this is not specified in the mutation operator. So 1, 2, and 5. Changes synaptic weight, exactly. So when we add a neuron, that neuron by definition, when we add a neuron, what is evolution doing? It's adding an element to the neurons list. So it randomly has to create a neuron. It needs to specify a threshold and a synapse and synaptic weights that connect this new neuron to existing neurons. So maybe they change the weight, but these synapses are created whenever a neuron is added. We add the neuron, and then we add as many synapses as we need to connect that neuron to all existing neurons plus itself. Okay, that one's a little tricky to tell. What about this step here? What mutation or mutations are being added to turn this robot into this robot? Two plus 8, yep. Logan had that too, 8 plus 2. So did Hannah and Missy. Yep, exactly, right? So 2 and 8 are applied at this step. At this step here, there may be some other mutations happening, but we see that at this step here, we are the most important one here, which now I can't find in this list. Aha, number 9, attach neuron to bar. This neuron has been attached to this bar here. And yeah, that's right. So now this particular bar here, we notice it's also split in 2. So it's hard to tell from this. It might be split bar into 2. It could be number 8. I apologize. This is a little unclear in the paper. But we can see now that this neuron is going to be treated as a motor neuron. So at each time step of the simulation, the value at this motor neuron is supplied to the piston or the linear actuator that's controlling this bar. And if this motor neuron value is positive, that means it's going to apply a force to extend the piston. If the motor neuron value is negative, that's a value that's going to compress or try and decrease the length of the piston. So we've now seen, or in your assignments, you're using hinge joints or that have rotational motors. They're applying torque or rotational force to try and rotate one object relative to another. Now we have a linear actuator or a piston where we're applying linear forces that pull or push the piston apart or together. Okay. I put my guesses down here. You can compare them against yours. Doesn't matter for our purposes if we got this exactly right. Just again, an exercise to build up an intuition for what is evolution doing in this case? How during the evolutionary process are mutations altering bodies and brains of robots as we go? Okay, so now we get to the fun part, having a look at what they actually evolved. Again, this is a somewhat older paper, so I apologize for the quality of the image here. What you're looking at here is a whole bunch of robots that are taken from a single generation. So they're evolving a population of these machines, and at a given generation, we can see the phenotypic variation in the population. Remember, phenotype is always the thing that's produced, not genetic variation. We can't see that, but we see the phenotypic variation. We have lots of different kinds of robot bodies in the population at this time. Here's a longitudinal cut through an evolutionary run. So now we're looking at the best individual in the population at generation 4, generation 60, generation 82, 117. And you can start to see evolutionary changes in the body of the robot. The changes aren't actually that large. You can see that this distant descendant of this robot up here, this distant descendant looks more or less similar to its distant ancestor. I think F is supposed to represent fitness, but that seems odd because the numbers seem very low. They don't seem to be increasing. So it could be that this is a non-functional mutant. So this is some node on the phenotypic tree of this ancestor, but it's not a very highly fit offspring. I think that's what we're looking at here. Again, it's not clear from the paper. I mentioned phylogenetic trees. This was something they included as a visualization in the paper. If you've ever taken a biology class, you've probably seen pictures that look very much like this already. Sorry, not phenotypic tree, a phylogenetic tree. So a phylogenetic tree is a great way to represent two features of an evolving population. It shows the variation in the population at a given time, which is shown on the horizontal part of the image. And then as we descend down through a phylogenetic tree, we can see how evolutionary changes occurring as evolution proceeds. There are different ways to draw phylogenetic trees. In this case, as you can see, it's hard to see the nodes because they're very, very small circles, but each node represents an individual, and a link connecting two nodes represents a parent-child relationship. So here's a parent here, child, grandchild, great-grandchild, and so on. The position of the nodes, the depth of the node is obviously which evolutionary generation was that robot born into. So it's something to do with the evolutionary age of that individual. The horizontal position between points represents their genetic difference. It's not perfect in this picture, but most of the time, points that are horizontally close to one another are siblings or cousins or second cousins or third cousins. And points that are horizontally very distant from one another have a very distant common ancestor. You have to go a long way back to find their common ancestor. So these individuals out here are not related to each other very closely, although I notice now I'm picking a bad example because this is not always true in a phylogenetic tree. These out here are still second cousins, but if we go deeper into one of these thicker trees, horizontal distance represents genetic distance. Okay. If you draw a phylogenetic tree like that, you can see macroevolution. You can see big macroevolution. So you can see big genetic changes in the population as a whole. Macroevolution is contrasted with microevolution, which we just talked about, which is sort of individual mutation events between parent and child. When we zoom out and look at the whole phylogenetic tree, we're looking at macroevolutionary dynamics. You'll notice that in this case, in this particular evolutionary run, they got some really nice genetic diversity. So at the end of evolution, they have a lot of robots in the population that only have distant ancestors. That probably means that these individuals are also quite structurally different from one another. So we get divergence here. We start to get lots of different kinds of robots. In the second evolutionary run, they got the opposite. They got convergence. So there were sort of different groups of robots that were moving relatively quickly, but probably moving in different ways. But those eventually all died out, and eventually there was only one small, there was in the population at the end, all of the robots looked and acted very similarly from one another because they were all siblings. They were all genetically very related to one another. In the third evolutionary run, you can see what the authors referred to as emergence of species. These aren't strictly species because they can still they can genetically recombine their material together. Species, by definition, cannot mate with one another and produce viable offspring. You can see at the end of evolution, there's 1, 2, 3 different groupings of robots. Within each grouping, the robots probably look and act similarly, but across these 3 groups, they probably look and act very different. You can see in D here, almost all of the robots were moving that had a particular structure and moved in a particular way. But in that population, there were 3 individuals that survived for quite a while and didn't produce any offspring. But then eventually these 3 started to produce offspring that moved faster than the dinosaurs over here, and these mammal robots gradually started to outcompete these much more common robots in the population and eventually drove them to extinction. And off we go. Okay. Again, this is a nice tool that you might want to use in your final project. You used matplotlib to visualize your sensor values towards the beginning of the course. You can go back and have a look at the sensors assignment to see how to draw things in matplotlib. You can record information now from search.py. You can write information out to disk and read that file back in and use matplotlib to visualize how things are evolving in your population. In the parallel hill climber, you're not going to get very interesting evolutionary dynamics. You're just going to get, if you have a population size of 10, you're just going to have 10 vertical lines descending the visualization. You can alter the parallel hill climber to allow genetic recombination, and then you start to get more interesting evolutionary dynamics. We'll talk about that next week when we talk about the final project. Okay, so let's have a look at some of the solutions. I think I can play, okay, good, I can play these in parallel. So here are 2 members of the same family tree. You can see they look similar and act similar. You'll notice that there is a regular oscillation in the pistons that is driving the locomotion of these robots. So that's the central pattern generator at work. Remember, the central pattern generator is supplying 12 regular pulses, and the synaptic weights inside the neural network alter how those pulses are translated into movement in the robot. And right at the end of this video, they actually drew the neural network in the simulation. Okay, one more time. Okay, here's another solution. Or here's another branch. Here's another family tree. These are clearly very different from the snakes. They're taken from a different evolutionary run. So just giving you a sense of the variety of form and the variety of function that the authors got in this experiment. Here's just some more interesting ones. You'll notice that bilateral symmetry isn't very common here. The left side of the body does not look like the right side of the body, although that's not always true. This was very early days for physics engines, so you can see there's a lot of inaccuracies here. There are parts that are interpenetrating with one another. The robot is kind of partly sinking into the ground. A lot of new technologies at play in this experiment, not just physics engines, but 3D printers, which we'll talk about in a moment. Okay. It's a lot of lead up for the reason we're talking about this experiment today, which is one of its goals was to try and cross the reality gap. In this case, they took 3 different robots, the arrow, the pusher, and the tetrahedron. And they took each of these 3 designs and 3D printed their plastic skeletons and then snapped in the motors and electronics. So let's play the arrow here. The video is a little bit sped up, so it looks visually like the physical arrow is moving faster than the simulated arrow. Actually moves slower. For the same amount of time in simulation and reality, the physical arrow moved half as fast as the simulated arrow. So we kind of half crossed the gap. We lost quite a bit of functionality in crossing the gap. In the case of the pusher, we lost even more functionality. The physical pusher moves almost a third as slowly as the, more than a third slower than what evolution predicted it would in reality. In the tetrahedron, they got within 10 millimeters of. They got within 1 millimeter of the correct behavior. Pretty amazing. The camera angle is rotated here, so they're moving. They seem to be moving in different directions, but you can see the way in which the simulated and physical tetrahedron move is very, very similar. There's the neural network again. Why did the tetrahedron succeed in crossing the reality gap and the arrow and the pusher failed? We spent a lot of time in this course now talking about robotics, actuation, physical simulation. Any ideas? Why does the tetrahedron, what is it about the tetrahedron and the way that it moves that makes its function more resistant to changes in the environment? Why is this behavior more easily transferable from simulation to reality compared to these behaviors? Missy says structural stability. What do you mean by structural stability, Missy?
So like it's self-supporting and doesn't really have the freedom to wiggle very much like the pusher and the arrow do.
Yeah, that's a good point. So you'll notice the tetrahedron is simple, right? There's just one motor at work here. The others have more moving parts. Actually, the pusher also has just one piston. The arrow has 3. So it's simpler, which makes it more structurally stable. It's stronger, and as Missy mentioned, it doesn't wiggle around as much. There isn't as much extraneous motion. Henry says a strong foundation. The polygon of support, remember our discussion about locomotion, is relatively large here. It's a big triangle. The center of mass of this robot always stays inside its polygon of support, which means that it is always statically stable. If you remember back to our discussion about locomotion, it's next to impossible for the tetrahedron to push itself over. That's also true, I guess, for the arrow and the pusher. Matt says more robust and less efficient. Matt, can you expand on your statement there?
Yeah, because the robot kind of has to push that entire triangle, so there's a lot of friction and surface area on the ground. But as everyone else was saying, that gives it a strong foundation and less ability to not. It's less error can happen in the way that it's set up, but it's not as efficient.
Yes, exactly right. As Matt says, it's more robust, right? It's less error prone. Matt also mentioned friction. So you'll notice that the triangle, obviously, it's moving over some relatively thick carpet, as you can see in the picture here. So there's a lot of high friction. If you look carefully, you'll notice that the angle at which this central piston in the tetrahedron pushes is more vertical than the pusher and the arrow. The pusher and the arrow are pushing more horizontally than the tetrahedron does. The tetrahedron lifts itself off the ground a little bit more than the other two do. It's a very subtle detail, kind of hard to see in these three videos. The fact that it's lifting itself up, it's reducing friction with the ground. It sort of lifts up its mass and then places its mass back down in another position while keeping its center of mass over its polygon of support. So as Missy and Henry and Matt have mentioned, it's got a more solid foundation, but it is also overcoming friction. It's not working against friction by pushing from the side. If you push from the side and there are differences in friction between the physical floor and the virtual floor, you're not going to cross the gap very well. You're going to be sensitive to the particular friction on which you are. But if you carefully lift yourself up and put yourself back down again, you are less prone to being influenced by surface properties. In the before times when we were all running around on campus in the middle of winter, you'd be moving quickly because you're late for class, and you'd suddenly step on an icy patch and your body would sense you're on ice and you start high stepping, right? You sort of, the way you lift and place your foot is much more vertical than you do when you're moving on high friction ground. If your stance foot pushes horizontally behind you when you're on ice, your foot is likely to slip out from under you and you're likely to fall. So you make yourself less affected by the surface property you're moving over if you take more vertical steps. You move more slowly because you're moving more vertically than you are horizontally. But you sort of decouple your dynamics. You're decoupling the way you move from details of the environment. This is very different from the noise experiment we just talked about, where they noisify things to force evolution to ignore certain aspects of its environment. This is focusing on how behavior can decouple your influence, your interaction with the environment. This is all anecdotal. It's very hard to say formally or mathematically why the tetrahedron did a better job than the arrow and the pusher, and that this inability to write down a formal description of what works and what doesn't is what makes crossing the reality gap so difficult. If we could describe mathematically how to produce robust behavior, we could include that mathematical description in the fitness function and evolve robots that move quickly and are insensitive to ground friction, motors, sensors, whatever other details are in the robot or in its environment. It may not be impossible, but no one's figured out how to do it yet. Okay, so that's crossing the reality gap. But again, another big focus in this project was this brand new technology, the 3D printer. I don't know if any of you have worked with 3D printers before, but most of them work in the following manner. There's a horizontal plate, and there's a jet that extrudes, in this case, thermoplastic. Thermoplastic is a particular class of plastics which have a very low melting point. So in the head of the printer, there's a heater that heats and liquefies the plastic. It extrudes liquid plastic, and when it's deposited on the plate or on the growing robot, the plastic cools and solidifies. This is a common way. This was the way to do 3D printing back in the day. There are now many different ways to 3D print various structures. You'll notice here you can see some snapshots partway through the 3D printing of I think it's the pusher. Yes, this is the pusher. You'll notice that depending on the 3D structure, the 3D printer also has to deposit some thinner material that acts as support for the pieces actually being printed. Back in 2000, they would then immerse this piece of plastic in a bath, which would slowly dissolve away the thinner plastic and leave the hollow cylinders behind. Snap in the motors and electronics, and off you go. You'll remember that this robot is made from vertices and bars. The bars themselves can lengthen and contract, and when they do, that means by necessity the angles of the bars that meet at a vertex, those angles have to change. How did they allow that to happen if they were printing one continuous plastic piece? Well, the authors told the 3D printer to create ball and socket joints that you see here. So you can sort of mentally simulate this structure in your head and see how this would sort of move, in just 2 dimensions. It restricts motion in the other two directions. This is a ball and socket joint. You can simulate linear joints and ball and socket joints in PyBullet, and again you can tackle this in the final project if you like, and I'll give you some instructions about how to do that next week. This is not unlike how your shoulder works. Your shoulder is a ball and socket, and depending on how the ligaments are placed, obviously we have much more freedom of motion in one degree of freedom and somewhat less in the other two. Okay. One of the visions for so robotics has come a long way in the last 20 years since this experiment. And one of the nice approaches to thinking about 3D printing robots is that it might make them a little bit more environmentally friendly, because you might be able to recycle some of the parts and feed the melted thermoplastic. You can see them, they're heating up the robot here. The thermoplastic is liquefying, and they're collecting it under this plate. That thermoplastic could be fed back into the 3D printer to print another robot. So there are now recyclable thermoplastics. And just for fun, the authors imagined creating the Terminator 2 robot. Okay. We got 3 minutes left, so I just wanted to touch on a couple of offshoots from this project. I'm going to play this video with the sound turned off. This was the Fab at Home project that was launched the year after the Golem Project. That's Hod Lipson, the author on the Golem Project that we just saw. Hod and his students asked the following question: could you create a 3D printer that prints out most of its own parts? So you'll notice this particular 3D printer here, it's made mostly from plastic, and most of the parts of the Fab at Home are sort of made from their own parts. By doing that, you can make it much more cost effective to make your own 3D printer and print your own things at home. We're not quite there yet, but we're getting closer. Back in 2000, you could only find 3D printers in research labs. There's now a Fab Lab here at SEM. So in the after times, when we all get back onto campus, you can go over to the engineering labs and actually ask for some time on the 3D printer and print them out at home. The idea at Fab at Home was to try and create an open source version of this 3D printing technology, where you could just download the instructions, maybe order the original parts, and then have the Fab at Home print out some of its own parts and make your own 3D printer. The idea was to make this very cost effective, so that hopefully Fab at Home could be like the original desktop computers back in the 80s, the personal computers, where everyone had their own computer and everyone was coding up and hacking those computers to see what you could get computers to do. Fab at Home doesn't exist anymore, but there are some other open source initiatives around 3D printing to sort of crowdsource 3D printing, get 3D printers out into schools, communities, homes, to see what the general public can do with them and really push where this technology can go. Okay, I think we will stop there for today. You have a quiz due tonight. You're working on the 10th and the final assignment. When we meet again next Tuesday morning, I'll talk about the final project, and we'll go from there. Have a good rest of your day, everyone. Thanks very much. Bye-bye.